Hey guys, my name is Autumn Miller, and today I'm here to discuss the effect of added metals on the crystal structures and material properties of gold alloys. This slide shows the most common form of gold alloy, commonly called yellow gold. The material properties shown to the left are for gold at 18 karat or 75% weight gold. There are many different forms of this alloy, but the most common of which is shown as 15% copper and 10% silver. When compared to pure gold, we notice an increase in the hardness of the material and an increase in the strength of the material, while a decrease in the density of the material. This slide is an example of 12 karat rose gold, which also has many different applications, but is most commonly just an alloy between copper and gold. When compared to pure gold, this alloy also has a decrease in density and an increase in hardness and overall strength. The next common alloy is white gold. The material properties on the left are shown for white gold at 18 karat with additions of palladium, nickel, and zinc. This alloy shows an increase in hardness and strength as well as a decrease in density. None of these deviations from pure gold are surprising, and it's the creation of these alloys to serve the purpose of strengthening gold for its use in jewelry and other technical applications, while retaining its properties of non-reactivity and, well, beauty. Next, we can see a comparison of the color of all of these common alloys. Rose gold was made to imitate copper. Now, you may ask, why don't we just wear copper rings if we want the color of copper? But anyone who's wore costume jewelry or even looked at the Statue of Liberty would know that copper is very reactive with water and will eventually oxidize and turn green. However, when you add gold in a copper-gold alloy, despite copper's individual reactivity, rose gold becomes very non-reactive, despite retaining the copper color. Yellow gold was chosen to imitate the original color of gold, while knocking down the purity for strength and reduction in price. White gold was created to imitate a platinum color. This may have been for aesthetics, while still wanting to wear a gold ring, as the price of platinum is less per ounce than the price of gold, and is actually one of the least reactive metals. Here we can see a comparison between all of the material properties of these common alloys. We can see that the ultimate tensile strength of white gold is actually more than yellow gold at the same level of gold composition. This might be because of the addition of palladium, which is also a very strong metal. We can see that rose gold in this model is significantly stronger than the other alloys. This is because it is modeled as 12 karat, which contains less gold by mass and more copper. This will take on more properties of copper, which is very ductile, and this is considered to have a higher tensile strength. We can also take a look at the 3D models for these alloys. They all have a face-centered cubic crystallographic structure as shown. In fact, all of the materials added to these gold alloys also have an FCC structure, likely so that these elements combine in a way that strengthens the final alloy. This rose gold model is comprised of 75% gold and 25% copper. Copper has an atomic radius which is quite smaller than that of gold, and this is reflected in the model. In the model of rose gold, we can see that palladium and zinc have similar atomic radii to the gold. However, nickel has an atomic radii comparable to that of copper. In our yellow gold model, we see a combination of silver and copper. It's unknown whether discrepancies in the size of atomic radii is important in determining mechanical properties of the material. However, difference in electron density and valence for these materials do affect the mechanical properties. We can see this through the most effective means of color, which is an interaction with the electrons on the surface of the material and the light bouncing off this material. This interaction changes depending on the composition of the material. But those are the common alloys. What about the uncommon alloys? Not a lot of people know that there are other colors than white, yellow, and rose gold. These alloys are actually very rare, and it's likely because the process to get the color of these material sacrifices the property of gold, which makes it good for jewelry. Purple gold, for instance, is considered to be very weak and porcelain-like. It's an alloy between gold and aluminum itself is not a very hard metal. But aluminum is also a gray silvery color, so why does this metal appear purple? This is a principle called plasmonic resonance, and it has to do with the free electrons on the surface of the material, which interacts differently with oncoming light depending on the composition of the metals in the material. On this slide, we can also see green gold. Green gold is a lot harder than purple gold as a gold, silver, copper, zinc alloy. This type of gold wasn't very popular in the past, and this was because one formulation of the metal that was historically used was actually toxic enough to make people sick. They have since reformulated the metal, but it is still pretty rare. Our next alloys are blue gold and black gold. Now, these two are rarer than purple gold and green gold. Blue gold is an alloy between indium and gold, but what is interesting is that indium and gold alone are softer than this alloy, and the mixture of the two metals creates a harder material with around the same properties of purple gold. Black gold is a gold-cobalt alloy, but it seems that the color from the black gold is actually due to the oxidized rhodium plating and not the alloy itself, which is only slightly darker than normal gold. As you can see from all of these examples, there is a lot of variation between color, mechanical properties, and crystallographic structure between only a couple of metals and their formulation of alloys. Although this presentation focuses on the formulation of gold alloys for the purposes of decoration and jewelry, there are so many possibilities for new alloys with wildly different applications. Metallurgy is a complicated science, but it's still very important to our modern society. Thank you for listening.